peptide or polyamide from your quiz is a polymer of amino acids. You don't need to worry about that. We're going to talk about peptides later. Each amino acid in this large molecule has a one-letter code, and this one's name is Darth Vader, if you have the one-letter codes. It doesn't look anything like a Sith Lord, but it does have lots of groups on it that can either gain a proton to become positively charged or can lose a proton to become negatively charged, like we talked about last time. So we did this just towards the end of class, and I wanted to spend a couple more minutes on it because I feel like this is kind of hard. Students have struggled with this in other classes. The more times you do it, the more likely you are to succeed. So let's just take a minute to work on this together. You've got a pKa table on the back of your quiz. The only pKa's that are not there are the pKa's for water and alcohols. That pKa for both of those is 16, and the pKa's for hydronium or protonated alcohols. We haven't really talked about protonated alcohols, but that pKa is around -2. Other than that, everything should be on the list. Just to remind you of how this problem is set up, I've drawn the molecule in its neutral form. We're going to put it in buffered pH, looks like 2. We're going to eat the Darth Vader peptide, and we're going to put it at pH 2 in our stomach. Your stomach's acidic. Those are the two sort of major environments. Your blood is pH 7.4, pretty neutral. Your stomach is pH 2, pretty acidic. So we're going to say we swallow the Darth Vader peptide. I don't know that I'd recommend that. What form does it take in your stomach? Now, the peptide's going to be pretty dilute in your stomach, so the pH of your stomach is going to determine whether groups lose their protons or gain their protons. So for some groups, we're asking, at pH 2, is there enough acid present to protonate something to turn it into a positively charged conjugate acid? Or we'll be asking, at pH 2, should something be deprotonated to get the negatively charged conjugate base? So look for both of those things. If something has a positively charged conjugate acid, it may not be obvious. You're going to have to think, can this group gain a proton to become positively charged? If something has a negatively charged conjugate base, you'll be asking, can this group lose a proton to become negatively charged? So go ahead and get started on that. Let's take, I don't know, a while on it, and then we can move on to some of the other stuff. I'm going to wander around while you're working. If you have questions, let's talk. Questions or issues so far? So you'll look at the pKa's. You can consider both. So if something is neutral and you add a proton, you're going to look for something that looks like that, but where the proton is added. Okay, a couple of questions while you're still working on this, a couple of questions have come up that are important. So there's some confusion over how do I know when an acid can lose a proton versus gain a proton? Is that more than just a couple are thinking about that? Okay, let's go through this with, say, this side chain here, which is an alcohol, this group here, okay? Now you'll notice, as listed above, an alcohol, I'll try to draw this here, an alcohol has a negatively charged conjugate base called the alkoxide, and that pKa that governs that process, losing that proton, is 16. But the alcohol also has a protonated form. This one is called an oxonium ion. And the oxonium ion has two protons, the blue one and the pink one. pKa 16 refers to losing the blue proton to go to the negatively charged alkoxide. pKa of -2 refers to losing the pink proton to go to the neutral alcohol. Okay? So if you're starting with the neutral alcohol, there's two ways you can go. You could lose a proton to become negatively charged, or you could gain a proton to become positively charged. Whether that happens depends entirely on the pH. Let me pause because I'm seeing some confused looks. So follow-up questions about what I just said. Yeah?
So when we're looking at the molecule, we're just assuming initially that it's neutral. So
Right.
based on the pH, we determine whether it's going to be protonated or not.
That's right. For each group that we're thinking about, each pKa we have on the table or have memorized, we start out with the molecule that's neutral, and then we ask, is it going to lose a proton to become negatively charged, or is it going to gain a proton to become positively charged? Yes?
So, for example, in like the histidines on the amino acid,
Yeah.
there's an acid on the back, but it has another hydrogen or a proton.
Yes.
And it says the pKa is 6.
Yes.
So how do we know what the pKa of that one is
Okay.
in comparison?
Good question. I will, and bonus points for knowing that that's histidine. How do you know that?
I just know the amino acid.
You just know the amino acids. Excellent. Okay. Yeah, nice. Sweet. That's good. I've learned the amino acids tons of times. I did stuff in grad school where I had to know the amino acids. You'll have to learn them as part of this class. If you already know them, that's good. I'll say more about this one. I want to, because that's important, but other questions about the issue of, say, an alcohol having multiple options. Yeah? Does every acid on this chart have a protonated form? The chart only shows the protonated forms. So the chart, notice that pKa's, and this is important, a pKa is always for the thing that's going to lose its proton. So the alcohol doesn't have two pKa's. The alcohol's pKa is for losing the proton to become the negatively charged alkoxide. The oxonium ion has the pKa of -2 for losing the pink proton. So that's one thing that's easy to get mixed up. The pKa always refers to the acid form losing a proton to become the conjugate base. Now there are groups, many groups on this structure that can gain a proton to become a positively charged acid. For example, an alcohol can, an amine can, this group can, and this group can. Carboxylic acids could too, they would need to get protonated on the carbonyl oxygen. We see that sometimes in biology, though we won't talk about it today, and you don't have to worry about it today. All right, other conceptual questions? Yeah.
So does this relate to the thing we talked about earlier, where it's like the pKa is greater than pH, then it doesn't lose the proton?
Right.
If the pKa is less than pH, it does lose the proton. But you just said that if it, I guess if it doesn't lose the proton, then it doesn't have a pKa, or did I misunderstand?
All right, you correctly summarized if pKa is greater than the pH of the solution, the acid form dominates. If it's less than, the conjugate base form dominates. Now, I didn't quite catch the question after that.
So, just a second ago, were you saying that if it doesn't lose its proton, it doesn't have a pKa, or?
I didn't say, what I'm saying is pKa's always refer to acid forms losing their protons. So I think what's getting mixed up here a little bit is some of you are asking, what is the pKa for this oxygen, this OH gaining a proton? And you could figure out that number. It would actually be called a pKb, where B is for base. But instead, we always define, we always focus on the pKa. In other words, this -2 is for how easy it is for this oxonium ion to lose a proton. If pH were lower than -2, the oxonium ion would dominate.
So if it doesn't have a pKa, then basically that's base,
So can you give me an example of something that doesn't have a pKa? Okay. I think you may be trying to find meaning where I didn't intend it. I guess what I meant is the pKa always refers to, on the chart, if you look at the chart at the end of the quiz, the pKa shown here always refers to the loss of that proton. Okay? So for example, for this imidazolium ring, pKa of pKa of 6, that refers to losing this proton to become neutral. Some people might ask the question, what is the pKa for this gaining a proton? And I understand what you're meaning, but that's the wrong question. It's what is the pKa for the positively charged thing to lose its proton? Yeah.
So in this case, with the alcohol group, it would be neutral
Right.
in a pH of 2.
Right, so in this case, the alcohol group should be neutral at a pH of 2. Here's how you make that conclusion. Start with the positively charged form. That pKa is -2. pH is 2. pH is greater than pKa. That means the proton's gone. So that means we should have the neutral alcohol. Now we're worried about, can the neutral alcohol lose its proton to become the alkoxide? We make a second comparison. pH is 2, pKa is 16. If pKa is greater than pH, the proton is still there. So we conclude the neutral form dominates. Yeah.
So it's referring to the level at which it would take to neutralize a conjugate acid or conjugate base.
The pH, is what referring to? Go ahead.
So like you said, the pKa at -2 is how hard it would be for it to lose that hydroxide and become the neutral form.
That's right. The pKa of -2 tells you how hard or easy it is for the oxonium ion to lose a proton.
Is it in reference to like the pH level? So like pKa is if the pH were at -2. Is that what it's referencing?
Almost. So what the pKa means, the pKa is literally the pH where you'd have a 1-to-1 mixture of acid and base forms. The pKa is the tipping point. When pH is equal to pKa, you have 50-50. If pH is less than pKa, you have all acid form. And if pH is greater than pKa, you have all base form. So think of the pKa as the tipping point in pH. If the pH is higher than the pKa, The base form dominates. Did that help? I heard somebody say, but maybe not. Yeah.
Sorry, I'm just so confused how we got to -2. So PK.
How is this pKa minus 2?
Yeah.
We're not talking about the pH here. We're talking about how strong of an acid this is. A pKa of minus 2 means this is a very strong acid. I'm not sure that answered your question.
Kind of. Yeah, I just didn't know like where it came. Like so, there's PK of 6 I know that, but I just don't know how it got.
Oh, the minus 2 I told you about over here.
Oh.
Yep. All right, others? We thoroughly confused? Yeah.
Okay, so if we're looking at the H2N, the one with the NH and the NH. So, oh.
Not that one?
Sorry, in the other corner.
This one.
Yes, the R. Yeah. So would this one be a 12, but it lost the hydrogen, so it would be negative.
Okay. So if you before we do that, are we good on the alcohol? If we're not good on the alcohol, it's not worth spending time on anything else. Let me draw it for you this way. I always, when doing acid-base stuff, I always draw an arrow from whatever I'm thinking about being the acid form to whatever the base form is. So in considering whether the alcohol can lose a proton to become negatively charged, I look at that pKa, I say it's 16, and then I make a judgment call at pH 2. Should that proton still be there? Well, 16 is greater than 2, so yes, the proton should still be there. Is everybody okay with that judgment?
So we're saying the conjugate base is RO. And it
RO
becomes-
minus, yeah.
it when it turns back.
Yep, this is for this comparison, for this pKa of 16, the neutral alcohol is the acid and the alkoxide is the conjugate base. Now, for the other comparison from protonated oxonium ion, this is the acid and this is the conjugate base, but that pKa is minus 2. Compare pH, which is 2, to the pKa of minus 2. If pKa is less than pH, the conjugate base form dominates. What is the conjugate base of the oxonium ion? It's the neutral alcohol. So we make the conclusion that the alcohol is neutral at pH 2. Yeah?
So like down on the bottom where you have this one here,
Yeah.
on the back there is like a molecule that looks like that that is protonated.
Right.
It has a
Right.
So when you were talking about it yesterday, you told us just to like ignore that. Like at what point would you then?
If you heard me say ignore what you just said, I was wrong. So the question is, and we'll do this with histidine too, the question is this functional group here is called guanidine, and there is no pKa value given in the table for loss of a proton to give you a conjugate base. We don't know what that number is. It must be high enough that it doesn't matter at physiological pH. If the pKa is in the 40s, who cares in biology because you can't get up to a pH of 40. So if you can't find the number on the table, and it's not one of these two that I told you to memorize, then you don't have to worry about it. Right. On the table, there is one where the guanidine is now the conjugate base of an acid form, which is like this. So that one you do have to pay attention to. That's a positively charged form. It's called the guanidinium. And again, this is the acid form, and its pKa is 12. So what do you conclude for that at pH 2? Is that proton still on or not? Yeah. In other words, At pH 2, if you started with the neutral guanidine, there'd be enough hydronium in solution for the neutral guanidine to deprotonate hydronium, pick up a proton, and become the positively charged guanidinium. That's one thing that some people are struggling with, like how does it happen and where do I get the proton? Well, at pH 2, you get it from whatever hydronium is present in solution. And we're just asking, and pH is a measure for how much hydronium is in solution. So by comparing pKa and pH, we're really just asking the question, is there enough hydronium to protonate this to get to its acid form? Yeah?
So just to clarify on that, so that's a good example for it actually. So when pKa is greater than 2 in this case, then it prefers the acidic state.
That's right.
But when it is lower than 2, it prefers the conjugate base state.
That's right. If the pH is 2, when pKa is higher than 2, the acid form dominates. If pKa is less than 2, the base form will dominate. Remembering that pKa is that tipping point. If pH gets higher than pKa, then the base form will dominate. Yeah? Am I recording already? Thank you, and yes. We're 20 minutes in, so it's a good thing we did.
I think the thing you told us to ignore was the and it's
Yeah. So I did tell you that in the peptide backbone, there are these functional groups that are called amides. And I told you that amide nitrogens are different from amines. So I told you don't worry about the amide nitrogens picking up a proton. In contrast, you do worry about amines picking up a proton. Yeah?
I don't think there's an example of this in this question specifically, but what if the pH and the pKa
Right. What if the pH and the pKa were
is the same?
the same? It would be 50-50. That'd be a tough question to answer, right? How do you answer, is it charged or not, when half of it is and half of it isn't? So I carefully write my questions to avoid putting you in that situation. I got you. Yeah.
Sorry, I feel like I understand the point where we're figuring out if it's on an acid or its base based on the pKa and pH, but what was the next step after that?
Okay, so after you determine based on pH and pKa whether we exist in a plus form or a minus form, the question asks you what's the net formal charge. So you just add up all the charges. Yeah.
Going back to the alcohol, when we're talking about the -2 and the 16, how do we decide which one we use?
How do you decide which one you use? In a sense, you don't. You have to memorize that -2 is for the oxonium ion that's positively charged, and 16 is for the alcohol. And then in terms of which one dominates, you simply look at the pH. If pH is less than -2, which it won't be in biology, the positively charged form will dominate. If it's between 2 and 16, the neutral form will dominate. If it's greater than 16, the negatively charged form will dominate. Yep. Okay, good. Yeah.
Okay, just to wrap up with the histidine,
Yeah.
so that would be in its neutral form?
Let's look at this side chain. Okay, so for this imidazole side chain, there is no pKa shown in the table for proton loss. So we're just simply not going to worry about that losing a proton to becoming negatively charged, okay? You might be curious about what that number is. It might be known somewhere. It's high enough not to matter in biology. However, the neutral imidazole has a positively charged conjugate acid, and its pKa, is 6. Here's the positively charged conjugate acid. Its pKa is 6. So now we're going to ask the same question. If pKa is greater than pH, the proton's still on, the acid form dominates. That means that this group here should be in its positively charged form because our pH is 2. Now histidine, this amino acid, which is called histidine, and that'll come up later. If you don't know that name, that's fine. That's an interesting one, right? Because its pKa is 6. If our pH were 7.5, what would the dominant form be? The conjugate base form, the neutral form. So histidine can change depending on whether it's in your stomach or your blood. It can be positively charged in your stomach. It can be neutral in your blood. All right. Carboxylic acids. You guys okay on those? No? Okay. That's fine. That's okay. I appreciate the honesty. I heard a talk when I went to see Amber talk at Women's Conference last Friday. At Women's Conference, they have 2 speakers per hour session and both get 25 minutes. There's a woman who spoke before Amber. I can't remember her name. Anna Lara something, Solomon, I think. She works up at Aspen Grove. But anyway, she encouraged the audience, when you say, "How are you?" to someone, don't respond fine if you were in fact not fine. And then she also encouraged people not to ask people, "How are you?" if you don't have the time, energy, or inclination to actually listen to an answer, which I thought was kind of funny. But in any case, thank you for saying we're not fine on that. So for the carboxylic acid, I told you there is, if the carboxylic acid were a conjugate base, there is a positively charged acid form, but the pKa is not shown. That must mean that it is low enough not to be important very much in biochemistry, so we're going to ignore it. Instead, what is the pKa for a carboxylic acid? 4, okay? Now, the values vary. For right now, we're going to oversimplify and just say that it's 4. So at pH of 2, and of course the negatively charged form is the conjugate base. So this is the acid form, this is the conjugate base. pH of 2, pKa of 4, which form should dominate? The acid neutral form, okay? And we've got several acid groups in our peptide that we can make a similar decision about. I think we've done just about everything. We got another guanidinium group, which we said should exist in its positively charged form because the pKa of that acid form is 12. What other one are we missing? The far left, you've got the amine. The amine is something that's like an alcohol. If you look in your table, the neutral amine can be the acid of a negatively charged conjugate base. The negatively charged conjugate base looks like RNH minus, and its pKa is 38. That's so high as to not be relevant biologically, but we'll talk our way through it. Then the neutral amine is also the conjugate base of the positively charged acid form, this ammonium form, and that pKa is 11. All right? So here are our tipping points, 11 and 38. If pH is lower than 11, positive charge form dominates. If it's between 11 and 38, which it won't be in biology, the neutral form would dominate. And if it's between 38 and whatever, which it will never, ever, ever be in biology, the negatively charged form would dominate. So what's the right form at pH 2? Okay, you missed it. Let's try again. pH is 2. If pKa is greater than pH, the proton is still on. Yep, got to be the positively charged form. That is because our pH is much lower than the pKa. So think of the pKa as the tipping point. If pH is lower than pKa, the proton is still on. If pH is higher than pKa, the proton is off. Yeah?
Just understanding the table in the back.
Yeah.
In our group, the
Yeah, so the R groups here, in the table on the back, the R groups are something that are carbon, but they're not lone pairs. Okay, so these numbers here are all down here that are 38 are all for the neutral amines. And that's another mistake people make is they use the wrong pKa. These numbers here are all for the neutral amines. And then these numbers here are all for the positively charged ammonium forms. This is exactly like the oxonium form and the alcohol, except it's the nitrogen analog, the ammonium and the amine. Okay. There's another one like this on the problem set. I can guarantee you that I will give you one of these on the exam. So it's worth working out and making sure you can do it. Let's see. Let's count up the charges then. I don't see any negative charges, right? And I see 1, 2, 3, 4 positive charges. So the right answer here is +4. Now, as a fun exercise, you should, and I will post this on the content page of Learning Suite, you should tonight or tomorrow, when you're spending however many hours you spend, what a semester to take 285, right? Spring term. You got to do it. It's going to be over soon. Go do the same thing at pH 7.4. Okay? Imagine Darth Vader got in your blood. That's a metaphor for what's happening in this class. I'm Darth Vader, and I'm infiltrating everything about your life because you're having to spend so much on this class. Sorry. But you don't know the power of the dark side. All right, good. Other questions about that? Practice that. Once you get it, it's going to be pretty easy in second nature, but struggling through it and reasoning through it is really important. And you got to build up the muscle memory to be able to do it under pressure. Okay. What I hear students say after the fact is, I thought I knew how to do this, and then I got in the testing center, and then I forgot or I struggled. And mostly that's a function of lack of practice. So let me give you just a story from my life on the importance of practice. We have all kinds of time. I was not really good. I am not really good at any of the sports. And so on my mission, this was a problem because the way the missionaries like to socialize, back then at least, was all around sports. So P days were all about get up as early as you can, go get the groceries and get the laundry done, and then get to the church as soon as possible to play hours upon hours of basketball. No, thank you. But of course, you know, I was just one nerd in a sea of people that liked sports. So what I would do when the companions and others were playing ball is I'd sit in the chapel and play the organ. I mean, that is super nerdy, but it's what I did. And so I played the piano before my mission. I taught myself how to do the pedals and there were some chances on my mission to play in various wards and branches. There was a sweet older sister in the Laredo 4th branch that wrote me a poem in Spanish, which she put in a scroll and rolled up in some decorative scroll container and handed to me. And it was about what a blessed son of our Father in heaven I was for for blessing their ward with the sound of music or whatnot stuff. So it did come in handy. But in any case, I've done it basically ever since I got back, ever since we've been married. Amber jokes that as soon as I say, oh, and I play the organ, that's the death knell, and I'm going to get that calling. So I've had it, and over the years, I'm not that good, but I'm passable if I practice. Over the years, sometimes the ward music person will say, hey, do you want to play a solo for Christmas? And I'm like, oh, that'd be fun. And so one year, I decided I was going to try something. And again, this is so nerdy, but you guys know one of the tabernacle organists. His name is Andrew Unsworth, and he's really good. And he had arranged something, a music song. We don't really it's not one of the hymns that we sing, but it's kind of a fun song called Ding Dong Merrily on High. I don't know if you've ever heard that song. He has some arrangement on the organ. I'm like, ooh, I'm going to do that. Well, it turns out when you're doing that, you're looking at now 3 lines of music instead of 2, and so my eyes don't stretch that wide, so you're constantly doing this, and you got the feet going. Anyway, I practiced, but I didn't have enough time to practice, and when I practiced, I would get to the hard part, or the part where I needed to change the stops to make the sound different by pushing a button, and that's when everything would really go off the rails, and I would have to pause, push the button, get my hands reset, and then go again. And I felt decently confident. I was like, okay, I can read the notes. Well, guess what happened in sacrament meeting? just like in my practice, I had to stop. I had to push the button. I had to look at the notes. I had to reset my hands. And I had to play and then screw up and then stop and reset my hands and do it again. In other words, in the fog of war, my preparation ended up being insufficient. So for you, the analogy is the testing center is your Christmas sacrament meeting. And you were performing an organ solo. You need to practice enough so you get it to muscle memory. I've done better solos since then, and it's always been I've practiced enough that I can get through it without stopping. So practice these kinds of problems enough so that you can do them without existential crises and long dark nights of the soul. If you're going to have those, better have them in the temple than in that place, right? Better have your existential crises outside of the testing center. All right. So it was good. We needed to spend time on that. What we want to do now is shift our focus temporarily to hydrocarbon molecules. We're setting the acid-base stuff aside, and we're going to think about molecules that have lots of carbon-carbon single bonds. And I'm going to show you some examples of this. This is an app called Molecules by Theodore Gray. And he's also written a book about the elements, and they have apps that you can look at. One of the neatest things about this app is you can look up different molecules, but you can also see real-life simulations of how molecules behave in solution as they're wiggling around. So I'm going to show you one of the simplest organic molecules. It's called ethane. It's CH3CH3. And can you guys see that okay? So that's two methyl groups bonded to each other. And the wiggling is basically how the molecule responds to kinetic energy. I can turn up the temperature and give the molecule more kinetic energy. You see it start to vibrate more, right? We'll turn it back down, cool it off just a little bit. Now, one of the things you can see if we do this is that it's kind of difficult to do. I haven't figured out how to do this very well. If I grab onto one of the hydrogens, one of the CH bonds, I can actually rotate around that bond like a propeller. Okay? Just spinning it around. Okay. Now watch as I do that. And we're taking a viewpoint where we're actually looking down the bond between the two carbons. As I do that, see if you can notice where it settles. Do you notice it always comes back to this point at which the CH bonds in the front sort of are staggered in between the CH bonds in the back? Yeah. That's realistic. That actually reflects what molecules prefer. The different shapes or the different rotations we can do around this bond are called conformations. C-O-N-F-O-R-M-A-T-I-O-N. Conformation. That refers to different shapes of a molecule, not different bonding, but just different shapes. And you can see that there's this characteristic low energy shape where the CH bonds in the front are sort of staggered in between the CH bonds in the back. And then if I get spinning really fast, how do we get back to the middle? If I get spinning really fast, you can see it passes through conformations where the CHs are all aligned, but those appear to be high energy because you can almost feel it going tick, 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 ka-chunk, and then settling to the one in the middle, right? No, you don't see it. Okay, I'll do the sound effect while it's spinning. Oh, dang. All right. Spin, spin, spin. Tick, 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 ka-chunk. All right, it's just like Wheel of Fortune. All right. So what we're looking at about this sigma bond between two sp3 hybridized carbons is called a staggered conformation. The high energy conformation where the CHs are all lined up, that one doesn't survive. That's called an eclipsed conformation where the CHs are all lined up with each other. Staggered is more stable than eclipsed, and the reason why has to do with the electrons in the CH bonds. Electrons repel each other the closer they are together. In the staggered conformation, the electrons in the CH bonds on the front carbon are as far apart as they can get from the electrons in the CH bonds on the carbons in the rear. So this staggered conformation minimizes electron-electron repulsion. We have a word for electron-electron repulsion in organic chemistry. We call it sterics. Sterics refers to large things with electrons wanting to be as far apart as possible. Let me give you a different view of this. Well, actually, let's just turn up the temperature. And as we turn up the temperature and we see the molecule wiggle, you see there's enough temperature now to rotate around that carbon-carbon bond, right? We're easily going from the staggered conformation, and I'm sorry, I can't hold it in the view where where the methyl group's in front, at least not very well, but you're getting the idea that as we increase the temperature, those little propellers are turning. This is true for sigma bonds in organic molecules at room temperature. There's enough energy for those methyl groups to be propelling around. So now, when you see a molecule with a methyl group on it, in the back of your mind, you need to be thinking, okay, I see the methyl group there, it's CH3, but it's not motionless. That little thing is torquing around like a propeller, all right? Another view of atoms that may be helpful to you, we'll look at the Spartan app, and I will draw ethane, and we'll draw a space-filling conformation. So this is the staggered conformation for ethane, and let me just, let's go space filling. This is how big the carbons are relative to the hydrogens, and adopting this staggered conformation is all about making sure that the bonds between the carbon in the front, the bonds between protons and carbon in the front are as far apart as possible from the bonds between carbon and the hydrogens in the back. Okay, questions about that? So ethane is as simple as it gets. Let's do a little bit more complicated. Let's work on your quiz question 2. We're going to draw the Lewis structure of the molecule called butane. So before you do that, let me just summarize on paper 2 conformations that we've talked about for ethane. Here is a structure of ethane. I'm going to use dashes or wedges. Dashes and wedges as appropriate. We're going to do what's called drawing a Newman projection. And a Newman projection is where you look down a bond between the 2 carbons in ethane. So this is carbon 1 and this is carbon 2. I'm going to put my eyeball in the plane of the page, and I can never resist the Sith eyeballs. Although last night, Amber and I watched an episode of The X-Files, which is this mystery show from the 90s, and there was a guy on it. Their monster of the week was some dude that was eating livers, and his eyes were like really yellow or something like that. So anyway, gross. Looking down the bond between carbons 1 and 2, and we're going to draw over here what we see. So in the front is carbon 1. And let's see, from our perspective on carbon 1, a proton would be pointing down, and then the one that's a wedge would be angled up out towards our right, and then the one that's a dash would be angled back to the left and upwards. Okay? Do you see that perspective? That should be analogous to the view we saw in Spartan. That's the view you're taking in the Newman projection. And then for the hydrogen in the back, oops, you can't, sorry, for the carbon in the back, I can't actually draw carbon 1 because carbon 1 is, I can't actually draw carbon 2 because carbon 2 is immediately behind carbon 1. What does the circle represent? The circle really represents this bond between 1 and 2. I'm drawing it like a cylinder, even though that doesn't make any sense. Bonds aren't cylinders, but this is how we draw Newman projections. That's how you know you're looking down a bond between two carbons. Okay, so the circle just represents the cylinder that is the bond between the two carbons. You can think of the circle as representing that tube in the middle. Where is the laser pointer? Oh well. The tube in the middle between the two carbons. So in the back, we can't see carbon 2 directly, but we can see what's bonded to it. There's the hydrogen that's in the plane of the page here, which from our perspective over with my Sith eyes would be pointing upward. The one that's a wedge would be pointing to our right and angled downward. The one that's a dash would be pointing to our left and angled downward. So that's the Newman projection, and this is the staggered conformation. And then if I wanted to draw an eclipsed conformation, which those eclipsed conformations are high energy, I could simply, with my imagination, rotate the carbon in the front, pull this hydrogen up so that it would be aligned with the hydrogen in the back. So the way I would do that is I would draw, and supposing we can label the orange hydrogen, and then this one is blue, we'll label the one there blue. If I rotated in this direction, the orange hydrogen in the front is now going to be eclipsed with the blue hydrogen in the back. Of course, if I drew it perfectly, you wouldn't be able to see any of the things in the back because they'd be totally covered by the things in the front. As it is, to make it possible to draw, we offset things a little bit. But this is an example of an eclipsed conformation. And this is high energy. And you can see that by rotating, if I continued to rotate, I could get to another staggered conformation where this orange hydrogen were now on the right side. Should we draw that? I could continue to rotate, and that would get me to a new eclipsed conformation. Where the orange proton is now no longer eclipsed with the blue proton. Okay, questions about that? Yeah.
So the third one is staggered, or is it?
The third one is also staggered. Yeah. So and for ethane, you can see that these two staggered molecules are two staggered conformations are entirely equivalent, but the eclipsed conformation is higher in energy. And in a way, the eclipse conformation is the high energy hill you have to go through to get from this staggered conformation to that one. Couple of terms that we will talk about. In a staggered conformation, protons that are adjacent to each other are said to be gauche to each other. Protons that are opposite each other, one on the front and one in the back, are said to be anti to each other. So we'll use gauche meaning they're side by side in the staggered conformation, anti meaning they're directly opposite each other in the staggered conformation. So the orange proton is gauche to the blue proton, but the purple proton is anti to the blue proton. Yeah.
Just to clarify, these are on the separate methyl groups, right?
These are the separate, yeah, so the blue proton is on carbon 2, it's in the back, and actually I'll highlight them over here. Here is the blue proton on carbon 2, here is the orange proton, and here is the purple proton. Yep. So gauche and anti refer to relationships between a group on the front and a group on the back. Are they gauche to each other or are they anti to each other? Okay, we got more to do there, but let's take a break, take 5, and we'll be back and get going again.